Okay, so today we will continue derivative stuff. So I have a quick slide of review since we covered a lot of ground yesterday, and now we're getting into really the meaty territory where there's a lot of results that one has to have kind of one access to in your mind. So this is a review of the last two sessions, more or less. And then today we're going to finish kind of the collection of standard derivative rules that everyone is expected to have memorized, basically. So I should preface this a little bit, because this is going to be crunchier than the stuff we've been doing recently, where by crunchier I mean there will be more calculations and fewer proofs. So this is closer to, say, the trig unit, for instance, where there were a lot of quick calculations that I asked you to just be able to do automatically, like sine of pi over 6 is a half or something. So well, I'm just warning you, because on the one hand that's good, because it feels good and satisfying to answer crunchy questions like this quickly, but you also have to remember to keep your focus on what's more important, right? So understanding the proofs and the big picture concepts are more important than being able to do the calculations. So do not allow yourself to get seduced by just knowing how to do the crunchy bits and not understand the details, because what's more important is seeing the conceptual picture. And that's just a broad warning. So we'll kind of get these important derivative rules, the power rules, the quotient rule, chain rule, and then do some blitz questions. That will be the plan for today. I have about 30 slides. So thoughts from last time, or questions about the roadmap or plan for today?
I do not have any thoughts or questions.
Very good. I like how you mix up your tone of voice when saying that you don't have any questions, because it's the same every time. Okay. Last time. Okay, so the important content of the last two meetings, more or less, was this definition of the derivative. So this was motivated by the question asked by Newton about thinking about the instantaneous velocity of a particle whose speed is changing, and it led us to this definition. We defined the derivative of a function in a as the limit as h goes to 0 of this difference quotient, which you remember is basically rise over run, f of a plus h minus f of a over h, if the limit exists. And then we introduced two pieces of notation, which I called the Newton notation. This is what Newton wrote, and the Leibniz notation, both of which mean the same thing. And in order to force you to, become fluent with both, I'm just going to alternate between using the two of them without warning you for the rest of forever. Then we amended our definition to tangent line. So I gave the shitty definition of tangent line a while back, which was about kind of just coming in and touching the graph of a function at a single point. This was our non-rigorous definition of tangent line. But then I said, hey, wait, that's not a very good definition, because even what we think of as the tangent line, say, at this other point, might accidentally hit the graph at some second point, right? So even though we want this to be the tangent line, that was not a very good definition of tangent line. So we fixed it and said the tangent line has to pass through this single point a, f of a, and also have the slope equal to the derivative if that limit exists. So that's what gave us a criterion to tell us whether there is a tangent line. If that limit does not exist, then the graph has no tangent line at that point. And the classic example is the absolute value, as we saw. Then we proved some stuff. We proved that the derivative of a function whose graph is a line, f of x equals, say, mx plus b, with a slope m, the derivative is always just the slope of that line. That was a good sanity check. And then we took the derivative of sine and showed the derivative of sine is cosine. That's a good thing. We proved derivative is linear, so if you take two functions multiplied by some numbers, take the derivative, you have this nice linearity property that we remember from matrices. So you could pull out a and take the derivative of f and just add it to b times the derivative of g. So this is called linearity, the linearity of the derivative, which really means you can think of the derivative as an infinite dimensional matrix, but more on that maybe sometime. Then the last and most important thing from maybe not most important, but most interesting thing from last time was this product rule. So I like to have a little chant inside my head to remember how this goes. The derivative of the product of two functions is the derivative of the first times the second left alone plus the derivative of the second times the first left alone. I've written them in the opposite order here for some reason, but of course you can add them in either order. So you just differentiate each one and multiply by the other left alone and then add them. Good. This is to remind you of this stuff. So has this dislodged any questions that were floating around but did not come to the fore until I told you some of the words?
Out of curiosity, you refer to the quote-unquote Leibniz, that is pronounced, d of f over d of x. You don't seem to use that for the remainder of the page.
So I use ddx down here for the line. So for instance, this ddx applied to the quantity mx plus b. So you can write df dx, which you can also think of as we think of it as an operate. And my pen doesn't work now. Every time I want to, here we go. So you can think of and it's still not working. 1 second.
I'm just curious if there's any value to the missing f.
Any value to the what? The missing f, you say?
Correct.
Yeah, I'm trying to draw, but there we go. Okay, so I'm trying to convince you that df dx is the same as what I wrote later, because often we will write df dx in a different way as d dx acting on f. Right, so these are two ways of writing the same thing. You don't think of this as a fraction of a number d times a number f over a number d times a number x. You think of this entire symbol, d dx, as an operator. So this is like a matrix. The notation is supposed to remind you of a matrix acting on a vector. So the whole thing, d dx acting on f, is an operator. So what I'm trying to tell you is that there was not a missing f later when I used it as d dx acting on this thing, because I've just written d dx of f, where now f is the specific expression mx plus b. So it's really the same thing. I've just plugged in a particular f.
Okay.
Good. Good question, though. Yeah, it's good notation, but it's confusing because it looks like a ratio rather than an operator. But that's a good question. Other questions on this stuff?
I have no questions.
Excellent. Okay, new things. Power rule. Okay, this is the thing which I will ask you to prove in several ways on daily challenges, because this is the thing where if you cannot prove this, then I've failed in my mission as a human. So first I'll present the theorem, and then we'll prove it. So here's the theorem. Let n be a natural number. So remember, this is, in my notation, this doesn't include 0. So n can be 1, 2, 3, 4, whatever. These are positive integers. So this is x raised to some power. So if n is a positive integer and f of x equals x to the power n, so this is like x or x squared or x cubed, whatever, then the derivative of f at a is given by that power n times the number a raised to the power n minus 1. So that means the slope of the tangent line to this curve at a point a is simply n times a to the power n minus 1, and that holds at any a in the reals. So this is the thing which people typically do not prove. They will stand in front of you and say, what you do, quote unquote, is you take the exponent and pull it down and subtract 1, and they'll present this as though this is a perfectly sensible thing to do. You pull down the n and then subtract 1. It's nx to the n minus 1, or if you plug in x equals a, say na to the n minus 1. So this is the way this is typically presented in a high school calculus class. So someone will show you this rule, then they'll say, hey look, here's some examples. For x cubed, I pull down the 3 and subtract 1 to get 3a squared. For x to the 7th, maybe now I pull down a 7, and you remember by linearity, if it's 5 times a function, then the derivative is going to be 5 times the derivative of that function. So I simply multiply the 7 by the 5 and get a 35a to the 6th, and so on. But, of course, knowing something without knowing why it's true is very intellectually dishonest. I think it's worse than not knowing it at all. So we're going to prove it in one way by induction, and then you'll prove it a second way, I think, by the binomial theorem, and possibly a third way. But first I want to remind you what induction is. We mentioned it very briefly in Chapter 1 in the proof stuff, and then I also mentioned it on the JT Math Club Piazza on Easter, in fact. I remember it was Easter. I posted an induction post about Gauss. So this is a style of proving a statement which must be true for all the positive integers. So induction is a type of proof that only works for statements that must be true for positive integers. And you want to prove it's true for all of the positive integers. And the strategy of induction is to prove that something is true for all positive integers by starting with a base case, typically 1. So you start and prove that it's true when n equals 1. and then you prove what's called the inductive step. This is the inductive step. The inductive step is you prove that whenever the statement is true for a specific number n, the statement is also true for the next integer n plus 1. So you prove that true for n implies true for n plus 1. And I think it's pretty clear that if you do both of these things, you can iterate that argument, and it follows that the statement will be true for all n, since we've proved it's true for n equals 1. And if it's true for n equals 1, it's true for n equals 1 plus 1, which is 2. It's also true for 3, 'cause it's always true for the next one if it's true for the 1. So that goes for all positive integers. It's kind of like recursion in programming, but backwards, right? You have a base case, and then you prove, you show how to build up to all of the other n's from the first one. So this will be our strategy to prove the power rule. We'll prove for n equals 1, and then we'll prove n implies n plus 1. So it's important to understand why this is a logically valid proof technique. So questions on induction, or thoughts on induction?
I do not have any questions or thoughts.
Okay, so you are convinced that this is a logically valid proof technique?
Yes.
Good, okay. Let us do the proof then. Alright, proof by induction. So we do first the base case, n equals 1. I claim we've actually already proved that this is true, because when we plug in n equals 1, the statement that we need to show is that when f of x equals x to the power 1, which is simply x, we want to prove, or want to show, that f prime of x, or f prime of a, I guess, equals, well, I just plug in n in the formula I'm trying to establish. So when n equals 1, this is 1 times a to the 1 minus 1, but a to the power 0 is simply 1. So we need to prove that if f of x equals x to the power 1, which is just x, then the derivative f prime of a equals 1. But we've already proven that, actually, because we've proven that for any line mx plus b, the derivative is m, and this is simply a line with m equals 1. So in fact, we've already proven this. The derivative of f of x equals x is f prime at a equals 1 for any a. And that's the same as the formula we're trying to prove. So we've proven the formula in this case, n equals 1, from last time. So that's our base case is done. Base case. Now the inductive step. So we're going to assume the theorem is true at a particular positive integer n. So we assume it's true for n. That means we can use it later in the proof, and we will. Now we consider the next integer n plus 1. So we'll define a function, g of x, which is x to the n plus 1. We have to compute its derivative. We're going to try to use the product rule, because you see that x to the power n plus 1 can be split as the product of these two functions, x to the n times x to the 1. This is just the way multiplication adds the powers, right? So the product of these is x to the n plus 1. So to apply the product rule and make it very clear what I'm doing, I'm just going to pick names for those two functions we're splitting it into to make it very explicit. So the first one, the x to the n factor, I'll call f, and the second factor, which is just x, I will call I for identity, because that's the identity function. So with that choice of notation, g of x is f of x times I of x, because that's simply, this thing is x to the n, and this is x. So now we use the product rule that we proved last time. So the derivative of a product, g prime, which is the derivative of f times I, we remember the derivative of f times I is the derivative of f times I left alone, plus the derivative of I times f left alone, just the product rule. Now I plug in the derivatives in each of those pieces. So the derivative of f, which is x to the n, here's where we use our inductive hypothesis. This is where we're using the assumption, using that it is true for n, right? Because we assumed at the beginning of this paragraph, suppose the theorem holds for n, because here, that assumption, if the theorem holds for particular n, that means if f of x equals x to the n, we are allowed to use the assumption that f prime at a equals na to the n minus 1. So we're assuming it's true for n and trying to prove it for n plus 1, and this is where we use the assumption that it's true for n. Because if it's true for n, the derivative of f prime of a, at a, is na to the n minus 1. So that's where we use the inductive step. The second piece is I of a. I of a simply means plug in a to the function x, so that's just a. Good. Next term. F of a, well, f is x to the n, so f of a is a to the n. Multiplied by I prime, well, I is x, the derivative of x is 1, so that's 1. Then here I'm just doing the multiplication of powers adds the powers rule again, so a to the n minus 1 times a is a to the n. The second term is a to the n times 1, which is simply a to the n. And then a challenge for you, what did I do in the last step? So what was the algebraic step I did to go from this line to this line?
I've already spent like at least a minute trying to figure out just that step.
What thoughts?
I was paying attention, but keeping that in the back of my mind.
What thoughts have you had over the course of that minute?
None outside of saying, I wonder if he accidentally somehow meant for that to be minus 1. No, that would be too easy.
Nope. Sorry, go on.
I see that this adds up to. I forget my addition of what's the name? A variable to the same variable to this power. I forget. Yes.
Oh, you forget the rule for. Okay, let me put it in.
Yes.
I'll put it in blue at the bottom here. So the rule is for any. I'll call it b because I already used a. For any b to the power r times b to the power s is b to the power r plus s, right? So that's the rule. So here, b, r, and s can be any real numbers. So do you see why this rule implies the transition from the second line to the third line, say in the first term?
Yes.
What are the values of b, r, and s in this specific case that makes it true?
For you have a, for r you have n minus 1, and s you have.
And s is what, you said?
1.
1, good, yeah. Exactly, yeah. So a is b, and then r is n minus 1, and s is 1, so n minus 1 plus 1 is n. So that's this piece. Good, okay. So second line to third line was using that same base, different powers addition rule. Do you see how I went from the third line to the fourth line?
That's the part I was confused about.
Let's ask a easier question. How would I go backwards? How do you expand this quantity a to the n times a sum of two terms? How would you algebraically manipulate to go upwards? I mean, is it not true that a times a quantity x plus y is the same as a times x plus a times y? You can distribute, right?
Okay. But why do I never bring graph paper down? Oh wait, back.
Yeah, maybe it helps to write it, but okay, yeah, so I claim to go from line 4 to line 3, we would just distribute the a to the power n, so you would a to the power n times the first one gives na to the n, and na to the n times 1 gives, a to the n times 1 gives a to the n. So I claim that this direction is distributing, so what is the word for going in the opposite direction, for undistributing a common factor of a to the power n?
Are you looking for the word factoring?
Yeah, this is factoring out. Good. So going from line 3 to line 4 is simply factoring out a to the power n. Okay, so what'd you say?
You mean to tell me it was that simple as dividing by an? Well, quote unquote dividing.
Yeah, not dividing, but factoring. Yeah.
Yeah.
Indeed. Did Corbin say something? I heard a quiet sound, but then I couldn't understand it.
He isn't here.
Oh, so he did not say anything. Okay, yeah, so besides algebraic struggles, to recap, all we did was split G into two functions, use the product rule. This was the product of numbers with the same base, add the powers. This was factoring out a sub n, or a to the power n, sorry. And then this last result is exactly what we wanted to show, because this is simply the statement that the derivative of x to the power n plus 1 is n plus 1 times a to the n, which is exactly the theorem's statement that we're trying to prove in the inductive step for n plus 1. So
Actually, I don't understand how that proves it.
okay, so we're trying, let me just erase that part. So in this inductive step, we were trying to prove that it's true for, well, let me write it out a little more explicitly. True for n implies true for n plus 1. So what does true for n plus 1 mean? True for n plus 1 means the statement of this theorem is true for the integer being equal to n plus 1. So the statement of this theorem, I'm just going to use g instead of f, but it's still writing the statement of the theorem. So what we need to prove is that if g of x equals x to the n plus 1, then g prime of a is what I've circled here up in blue, but with n replaced by n plus 1. So we need to prove that this... Oh, now you see it?
Yeah.
Okay, good. Yeah, it's just plugging in n plus 1 for n. So, good. Alright, very good. So I claim that actually proves it for all integers, because we proved it for 1, or all positive integers, sorry. We proved it for 1, therefore we have proved it, we've proved it for 1, and we prove when it's true for 1, it's true for 1 plus 1. When it's true for n, it's true for n plus 1, so it holds for all integers. Quite important to understand this proof. I'm probably going to ask you to rewrite it, and then ask you to rewrite it in a different way that doesn't use induction to make sure this is clear, because if you apply this without knowing why it's true, then you are lost. So, questions on this?
I do not have any questions. I think sometimes it might be easier to start out with like the obvious or simple things if I'm confused, because those are get hooked up on.
Oh, by those you mean that the algebra is usually the stuff that's more confusing than the big picture of the argument? Is that what you're saying?
I believe so, because as I realized, like while entire inductive step process, that it was just because of n plus 1 being replaced.
Okay.
I don't even know.
That makes sense. So I guess there's two ways that we could fix this. One, well, we could do both, but one is that I can ask more just concept checking questions, like as we're going through asking small questions about intermediate steps to see if you could explain why they're true. And two is that you can interrupt me more frequently when something is unclear and ask why something is true if you don't see why it is. I'm actually more happy about option 2 there, but we can do both of them if you prefer.
I guess option 2, but I don't like interrupting.
Well, you should. I mean, it's better to learn with back and forth, because then it's more of a conversation than a monologue. So interruptions are very welcome. Do you have other suggestions for things I could do to make those algebraic steps that you're getting hung up on more clear? Like, should I emphasize the reasons more when I write the slides, or like what would help with that?
I don't know. I guess what you just said might work, but
Okay.
it seems like a lot of the algebra steps are super simple and would be like one extra sentence.
Yeah, it's probably not bad. I'll try to add more detail going forward. The problem is I just often don't think of it. But okay, good. Sweet. Onward to using this now. Okay, so the context for this is a question from the Harvard MIT math tournament. So this is a math tournament for high school students where the questions are written by math majors at MIT and Harvard. So it's just like the math competition at Lehigh or at Bloomsburg, but this one is at either, it alternates, Harvard one year, MIT the other year. And what's different about this math competition compared to other high school math competitions is this one has calculus questions. So this is a math competition question that involves calculus from HMMT. So I will ask you to walk me through your thinking. So we're handed a function f of x, which is this sum of, monomials. So it's a polynomial, 1 plus x squared plus x cubed plus dot dot dot, all of these powers, up to x to the power 100. And we're asked, what is the derivative of this function at 1? So what's the slope of the tangent line to this graph at 1? So what do you think the first thing we should do to tackle this is?
Well, I have the answer, but I guess we have to prove it.
Oh, if you have the answer, tell me that first. I'm curious.
Is it 1?
No.
Darn. Seems like... Oh, wait, no, it's... Wait. Let's see. So we have to let x equal... I mean, you could let x equal 1, but no.
Well, this is a very important point. When you take a derivative, so say... Let's just do a simpler case. F of x equals x squared. And if someone asks you what is f prime of 1, there's two ways you could do this, and one is right, and one is wrong. This will always give you the wrong answer. Let's do the wrong way first. The wrong person says, well, I need to plug in x equals 1, and then I take the derivative. So this person says f of 1 equals 1, and then I take the derivative of a constant, which is 0. So he says, the derivative is 0. The right way is you say, well, the derivative of x squared by the power rule is this stupid thing about pulling down the exponent. So f prime of x is 2x, and then I plug in the particular value x equals 1. So I get f prime of 1 equals 2. So in fact, 2 is the correct answer, and 0 is not the correct answer. And the reason is, you probably see now fairly obvious, that if you plug in the number first, when you plug in a number to a function, you always get a constant out. So if you plug in first and get a constant and then differentiate, you will always get 0, which is usually not the correct answer. So you should always differentiate first and then plug in if you're given a constant at which you want to evaluate the derivative. Does that make sense?
Yes.
Okay. Good. Okay, so back to this thing. So what's the first step if we're going to differentiate this bad boy?
Does it have slope? Excuse me. Is it going to be 101?
No. But let's try to actually compute it. Let's work out the steps instead of guessing the answer. So what's the first step to do this?
Wait, no, now I realize that my answer still makes no sense.
So how do you take the derivative of each of these terms? Let's start with that. So what are the derivatives of each of these terms in the sum?
I'm going to use the thing that we proved, which is na to the power of n minus 1.
Good. Okay, so let's do that in each case. So the first one is the derivative of 1, which is what?
That would be 1.
1's a constant. What's the derivative of constant? So that's 0, right?
Okay.
Remember, we proved the derivative of mx plus b equals m. So the derivative, this is a line with slope 0, 0x plus 1, right? So the derivative of 1 is 0. Good. Okay. Next one. What's the derivative of x?
Just over here suffering.
What did you say?
Oh, excuse me, I believe that this is going to be 1.
Good. Alright, what's the derivative of x squared now?
Is it 2x?
It is 2x. Good. Let's keep going. What's the derivative of x cubed?
3x is to the second.
3x to the second. Okay, good. So Now, I'll put the dot 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 in, but I think you know what goes in the dot dot dot, right? There'll be the derivative of x to the fourth, which is 4x cubed. There'll be a derivative of x to the fifth, which is 5x to the fourth, and dot dot dot. And then what's the derivative of x to the power 100?
To the power of 99.
100x to the power of 99. Good. Okay, so we remember to differentiate first and then plug in. So now we are asked to plug in the particular value 1. So everywhere you see an x, in the previous line we replace a 1. So what is the sum? You don't have to add them up yet, but what are the numbers I should add after substituting 1 for x?
You're going to have 0 plus 1 plus 2 plus 3 plus all the way up to
plus up to 100. Good. Okay. Now, do you know how to add up the first 100 integers? Have you seen this trick before?
Is it 100? Well, referring to the statistics book I got, would this? No, that's multiplication. Never mind.
So you don't know the trick.
I don't.
Okay, so the trick is to think about pairing these up. So I'm going to write the last few numbers for you. So before we get to 100, there's...
This makes sense.
You see what I'm saying? Yeah, 97, 98, 99, 100. So I pair up... different color. I pair up 3 with 97. That gives me one copy of 100. I pair up 2 with 98. That gives me a second copy of 100. I pair up 1 with 99. That gives me a third copy of 100. So how many... Be careful, because there's one number I claim in here that doesn't get paired. So how many pairs do I have constructed in this way?
Would there be 49 pairs?
Good. Yeah, 49 pairs, because 50 is all by his lonesome. So
What about 100 itself? Oh wait, that's another. It's not a pair, but it's a thing.
Yeah, there's a so I shouldn't have said one unpaired. There's two unpaired numbers, but there's one unpaired number in this blue section. Yeah, good. So 49 pairs times 100, and then we add 50 because 50 is unpaired. Then we add 100 because 100 is unpaired. So this is the hardest part because we have to do arithmetic. This is what 4900 plus 50 plus 100. So what is that? 5050? Am I doing that right? Or 5050?
Correct.
Okay. Good. And you can actually prove there's a general formula that the sum of the first n integers is always n times n plus 1 over 2. So to check that we got the right answer, let's plug in n equals 100. So this should be 100 times 101 over 2, which is 50 times 101, which is, I believe, 5050. Good.
Seems reasonable.
Good, so this is the right answer. I just realized I have a typo on the next slide, because I think Yep! I forgot 100. So in my solution, I added the numbers up to 99 and forgot about 100. Interesting. Okay, so this should... I'll just append an extra 100 everywhere, and this should really be 50-50. So thank you for making me correct that. But okay, so just to review, what did we need to solve this problem? One, we had to know the power rule, apply the power rule to each term in this sum. Then you plug in a equals 1. That gives you the sum of the 1, 2, 3 up to 100. And then you use this pairing trick, or else you have memorized this sum. If you do math competitions, this is something that will come up all the time, and you're expected to have this memorized. If you don't do math competitions and you just are a normal human, then when you need this sum, you can either look it up or you can rederive it using the pairing trick, which is what we just did here. But that was back in 2.1 on the Math Club Piazza. Okay, questions on this?
Nope.
Okay, good. Pat yourself on the back. You have now solved your first problem from a Harvard-MIT math tournament question, which is good. This is something written by a math major. So excellent. Well, I guess you've been solving questions written by an ex-MIT math major this whole time, so maybe that's not really anything new, but This one was official.
I've never thought of that before. Jesus.
Yeah, I mean, I don't know if it's better or worse that theirs is official, but okay, another challenge. So this one will be a little more careful. Instead of just blindly applying the pulling down rule, I will ask you to look at each of the following functions and then decide whether we can take the derivative using the theorem on the previous slide and anything else we've proven so far. So that means for some of these functions, the assumptions of the theorem we proved are true, and we can apply the theorem to take the derivative. For some of these functions, the theorem will not apply because one of the conditions is not met, and I'll ask you to explain why the theorem doesn't apply. So let's go down the list. So for the first one, do we know how to take the derivative of this one, 3x to the fourth?
Yes.
Good. What is it?
12x to the third.
Good. You have already mastered stupid mnemonic. Okay, how about this one? Do we know how to take the derivative of 5 to the power x?
Will it simply be x?
Ooh, interesting. Why do you say x? What'd you say?
Oh, it would be x5, x minus, x, excuse me, x 5 to the power of x minus 1.
Let's back up. Theorem. So if n is an integer and the function is x raised to the power of an integer, then we know how to take the derivative. Notice this is x raised to the power of integer, which is different from integer raised to the power of x, right?
I'm going to say how we don't know that x is an integer.
Yeah, so it doesn't actually work here. The point is that we can do x to the 5, that's fine. We don't know how to do 5 to the x. If I shouldn't use an x, I should write note, but yeah, so we've only proven if it's x in the base and an integer in the exponent, not if x is in the exponent. Good. Okay, so well, I've already told you, but accidentally, that we can do this one, so what's the derivative of this one?
Yes, 5x to the fourth.
Good. How about this one? Can we take the derivative of x to the power minus 2?
Our n equals -2 is not the natural number, so no.
Good, yeah. So we only proved that this was true for positive integers. Here, -2 is in the integers, but not in the naturals. Good. How about this thing? Can we take the derivative of this using the theorem and any other results that we have so far?
I believe we can.
Okay. What's the derivative?
It's just going to be very painful.
Oh, I mean, it's not that bad. Just do it in 2 pieces, right?
Oh, have we proven that the derivative of an addition? I don't know how to word this.
Is the derivative of sum the sum of the derivatives, you're asking?
Yes.
Yeah, so clear back.
There it is.
Here it is, right? So this is linearity, right? The derivative of a sum of 2 things is the sum of the derivatives. So we proved the derivative is linear, right? So back to this guy. So can we use that to figure out what f5 prime should be?
I believe that we can let x. I think for how to do this right. So do we have an a and a b to account for in this case?
I guess there's a constant multiplying this thing. A is -2, if that's what you're asking for.
So, oh yeah, that makes sense anyways. So is this going to simply be -4x plus 3x to the second?
Yeah, -4x plus 3x squared. Good.
Whoa, it worked.
Yes. I mean, I share it.
Stream intensifies.
Yes, this is it's nice that this is linear. You can just add them up. But yeah, I will try not to ask too many questions like this, because I don't think there's much to gain intellectually from just applying the rule over and over once you know how to do it. But when you actually solve like concrete computational problems, like, I don't know, later we'll ask questions like, you have a sphere and the radius of the sphere is increasing at a rate of, I don't know, 5 meters per second. How fast is the volume increasing? And then you're going to have to do things like using this power rule. You'll say, well, okay, the volume of a sphere is 4/3 pi r cubed. Take the derivative with respect to r. That gives you 4 pi r squared, and so forth. So you just have to have memorized that you do this thing about pulling down the 3 and subtracting 1. Good. Other questions on this slide before doing Act 2?
I have no questions.
Excellent. Okay, so, well, these are the answers which you just told me, which you don't have to go through, I think, because they were all correct. So let's move on to, there's no name for this rule, I just call it 1 over f, because we're using it as a lemma, and intermediate results get to the quotient rule, which is more important. So, to emphasize the takeaway from that previous example is we know how to differentiate x raised to a positive integer, but we don't know what to do when x is raised to a negative power, like x to the minus 2, so that which is the same as 1 over x squared. So we need a new theorem to differentiate x raised to positive powers. And I'm going to be a little more general and tell us how to differentiate any function g which is raised to the power minus 1. Right, so this is the inverse, the multiplicative inverse, not the inverse function like f inverse. This is 1 over g for any function g. So I'll just read it. Here's the theorem. If g is differentiable at a point a, and g of a is not 0, so we can divide by g of a, then the function 1 over g is also differentiable at a, and its derivative is given by this formula. The derivative of 1 over g at a is minus the derivative of g at a divided by g squared. It's minus g prime over g squared. A mnemonic to memorize this. I will emphasize that the sentence I'm about to say is not an explanation for why this is true. We still have to prove this, but it is a mnemonic. Can I even spell this? Mnemonic to memorize this is that if you think of this as the left side 1 over g, writing that as g to the power minus 1, right? Because 1 over g is the same as g raised to the power minus 1. You can think of this as saying, well, we take the derivative of g to the power minus 1, and that's minus 1 times g prime times g to the power minus 2, which is the same as minus g prime over g squared. And this looks just like the power rule we just derived, except with a negative 1 as the power. Right, because what we did in the mnemonic was pull down the minus 1. That's where this negative sign comes from. And then we have a g to the power minus 2 left from subtracting 1 in the exponent. So that's why there's a g squared downstairs. And then you're left with taking the derivative of g. The only thing to remember is that now there's a g prime in the numerator. So again, this is just a mnemonic. This is not why this is true. This is just if you want to remember why there's a minus sign, why there's a g squared downstairs, you think of this as kind of like the power rule. Pull down a minus 1, here's the minus 1, then you subtract 1, so there's a minus 2 here. And then just remember there's a g prime upstairs. But anyway, we have to prove it. I mean, the mnemonic isn't a proof. So the proof will, of course, use the definition of the derivative. So the proof will need 2 parts. The first part is covering our asses to make sure everything is well defined, because we have made the assumption that g is not 0 at a. So we are allowed to divide by g of a without problems, because we know g of a is non-zero. We're always afraid about dividing by 0. The problem is that when we write down the definition of the derivative down here, we need to take 1 over g at 2 different points. You have to take 1 over g at a, which we know is fine, because g is not 0 at a. But we also need 1 over g at a plus h. And we have not assumed that g of a plus h is not 0. So we're worried that what if g at a plus h is 0, so we accidentally divide by 0 in this first piece. We have to check that that won't be a problem. So the first step will be check that that thing is non-zero, g of a plus h is non-zero for sufficiently small h. And once that's true, we'll just do the computation. We'll compute the limit which defines the derivative. This is the definition. Sometimes I use 3 lines for definition. This is the definition of 1 over g prime at a. So we'll just compute. Okay, questions on the roadmap of how we'll prove this?
I do not see why we must show that g of a plus h is not equal to 0, since we are not dividing, it appears.
Ah, we are this.
Now I see.
Yeah, I've used this. I find this kind of confusing notation, but this really means 1 divided by the function g evaluated at a plus h, right?
That makes sense.
Okay, yeah. So we have to make sure that's not not ill-defined. Good question, though. Important to understand that we have to make sure nobody divides by 0. Other questions?
No question.
Onward. Okay, first part.
How do you say awkward instead of onward?
Oh, no. I would like more questions, but a lack of questions does not make it awkward, in my opinion. I don't know. Just onward. Okay, so we've actually done a proof very... Ooh, that's not what I want. I want pen. We've actually done a proof very similar to this before, which is just the proof that if a function is continuous and it's non-zero at some point, you can find a neighborhood, which is an open interval, around that point where the function is also non-zero. So let me make that a little more precise. Here's what we'll think of as g of a. And so the first thing we have to say is that we have to argue for why g is continuous, right? But we proved last time that whenever, or maybe 2 times ago, whenever that was, whenever a function is differentiable at a point, it is also continuous at that point. So we know we have full epsilon delta power over this function. We have, we can do whatever we like because we know it's continuous. So now we're going to try to use our trick of choosing epsilon bars to find a region where this function is non-zero. And then we're going to try to push a plus h into that region so we know it's not 0. How do we do that? Well, we know g of a is non-zero. So we're going to choose our epsilon to be the absolute value of g of a over 2. So here's going to be, say, g of a minus epsilon and g of a plus epsilon. We're just choosing the value of epsilon so that everything within these bars at distance epsilon from the output are forbidden from hitting 0. Right? Because if epsilon's half this distance, g of a, and you never go half that distance back downwards, you're never going to hit 0. Okay. Now we use the continuity assumption. So we've assumed it's we've proven, I should say, we've assumed it's differentiable, so we've shown it's continuous, and if it is continuous, for any epsilon we can find a delta, so that when x minus a absolute value is less than delta, we have g of x minus g of a absolute value is less than epsilon. So find that delta, and then we pick our delta interval around a. So there's an a minus delta and an a plus delta, and we are now guaranteed that everywhere, I'm just picking random points, I don't know what the function actually does in here, but we're guaranteed that it never wanders outside the bars if you're in the interval a minus delta to a plus delta. And now we know, you've made this argument before, I think, in 1c of consolidation document 2, that you can use the reverse triangle inequality to bound this thing and show that this means g of x absolute value is strictly greater than 0 inside this interval. So the picture I've drawn where this thing never hits 0 is justified. Now for the last step, what about h? So now we've proven that if h is smaller than delta, so that a plus h lies in this interval, then g at a plus h will be non-zero, so 1 over g is well defined. How do we know we can take h less than delta? Well, the point is that the derivative is defined as a limit as h goes to 0. And the definition of the limit only asks for some delta, given an epsilon, some delta, such that the output of the function is epsilon far from the target. So this is kind of like when you do an epsilon delta proof and you make an initial assumption, right? Like you make an initial assumption, say delta 1 equals 1, and then you do some work, and then at the end of the day you say, well, I'm going to define my delta to be the minimum of delta 1 and my other junk. Right? You're always allowed to make extra restrictions on delta. So now you can imagine whatever argument you make when you restrict your delta, you should just also make the restriction that the h, I shouldn't call it, I've used the letter delta in two different places. This should really be, yeah, damn it. Well, there's two different choices of delta. There's the delta I use to define this interval. Let me call this delta tilde. This is, I should have thought further ahead. The delta defining the interval is now delta tilde. I apologize. So just imagine that when you make the argument in the limit as h goes to 0, you're going to try to prove that you can pick delta small enough to make some epsilon argument. You will simply insist that the final delta that you pick must be smaller than this delta tilde, so that h lies within this interval. And then 1 over g is well defined there. So, sorry, I kind of cocked that up, but the point is that g is differentiable, g is continuous, we can pick bars such that g is therefore non-zero in an interval, and then since we're taking a limit as h goes to 0, you can simply restrict h to lie in that interval. That's why it's true. Okay, questions on this?
I have no questions.
Okay. You're being generous to me, since that was a not very lucid presentation. Okay. Now this part's just algebra, so no epsilon management here. So we have proven that 1 over g is defined, which is to say g is non-zero when h is small enough, when it's in that interval. So that part's done. Now we just compute. So remember, we're trying to take a derivative, so we use the definition of the derivative here, which is, f at a plus h minus f of a over h, but here f is 1 over g. So we want 1 over g at a plus h minus 1 over g all over h, limit as h goes to 0. The first trick, which is multiplying by 1, is very common whenever you have a fraction of fractions. Right? Whenever you're doing a derivative proof and have fractions upstairs, you normally want to do this trick where you multiply by 1 in the particular form that will clear the denominators. What do I mean by clear the denominators? I mean, we multiply by 1 in the form of the product of the two denominators in the upstairs. So I'm multiplying by g of a plus h over g of a plus h, because then when I multiply by these, distribute, I guess, when I distribute these two factors in the numerator, you can kind of see g of a plus h times the numerator, so I'm just writing the numerator, not the denominator here, 1 over g of a plus h minus 1 over g of a. I distribute this in the first term, g of a plus h over g of a plus h cancels, so I'm left with g of a. In the second term, g of a over g of a cancels, and I'm left with g of a plus h. So when I distribute in the numerator, I am simply left with g of a minus g of a plus h. So that's the only algebra trickery in this calculation. So is that manipulation that I just did clear, or was that too fast? What is it? Oh, you said clear?
Yep.
Good, okay. So that's the numerator. Denominator was easy. I just moved this over and multiplied by h. So now there's an h, g, a plus h. Now I have to justify this step, because here I'm splitting the limit into two pieces. We are only allowed to split the limit of a product into the product of both limits if both limits exist. I'll tell you why the first limit exists. This limit exists because we have assumed that g is differentiable at a. And the first limit up to a minus sign, notice g of a plus h and g of a are in the wrong order upstairs for it to be a derivative. The derivative is supposed to be g of a plus h minus g of a, but you can just factor out a minus sign. So if I factor out a minus sign, this first piece is just the derivative at a, and we have assumed that that limit exists because g is differentiable. So challenge for you, why do we know that this limit exists? Why does this exist?
because we have shown before that g of a does not equal 0 and g of a plus h, we set up in such a way that does not equal 0.
Good, we do need that. So those two assumptions tell us that this fraction is well defined. Right, so this thing is not going to be 1 over 0. Good. So that's the first step. The second step is once you are convinced that this fraction is non-zero, how do you know that the limit of this fraction exists? Right, it's possible for this denominator to be non-zero, but the limit might still not exist. Like, if it were something complicated like a stars over Babylon or something, right? Stars over Babylon never had a non-zero denominator, but the limit still didn't exist at certain points. So how do we know the limit here as h goes to 0 exists? We proved some theorems about this you'll have to tell me about.
Actually, I have I believe, unrelated question. Do any polynomials have the to the power of -1, like, component?
Do any polynomials? Oh, so you're asking, can I write a polynomial like f of x? And my pen just died. Son of a bitch. There we go. You're asking me, can I write a polynomial which is like 1 over x plus 5 plus x? So like an ordinary polynomial, but it has some terms that have negative powers.
Right.
Yes. That's a very good question. This is something called a Laurent series, named after the French mathematician Laurent. So a polynomial that has some negative exponents, like 1 over x or 1 over x squared or 1 over x cubed, whatever, you can have as many of them as you want, but that is a generalization of a polynomial called a Laurent series. So of course, you have to be careful with these functions because they blow up at 0. Right? You can't plug in 0. These aren't well defined everywhere. So a Laurent series is not continuous everywhere like a polynomial is. Right? Polynomials are continuous everywhere. This obviously isn't. But even though they're not continuous everywhere, you can play some mathematical games and still extract useful information from them, even though they're not well defined everywhere.
I make a proposition.
Proposition. What is your proposition?
Can I say that this may abide by the laws of polynomials? How do I word this right? What we're looking at right now is 1 over g of h, and we have already considered that the denominator does not equal 0. So, relate to the same rules as a regular polynomial, where that must.
We don't need to know it's a polynomial, but just your argument's almost right. Let's just fix one piece. So we don't need g to be a polynomial, but what conclusion about polynomials are you using in your argument? What do we know about polynomials that you're using when you just said that?
That polynomials are continuous.
Good. Do we know g is continuous?
Have we said this before?
Well, we know g is differentiable, right?
So yes.
Good.
G is continuous because it is differentiable.
Okay, good. So amend the argument you just made, which was almost correct, so that it doesn't use the polynomial argument, but it just uses continuity.
I don't see how to do that.
Well, so we proved this theorem that if a function is continuous, the inverse 1 over that function is continuous everywhere the function is non-zero, right?
I have no memory of this.
This is in one of the later chapter 2 things. So, well, okay. Yeah, that's fine. But the argument to make here is that g is continuous, and we know, as you said in the first part of your answer, g of a and g of a plus h are both non-zero. So this whole expression is also continuous because it's 1 over a continuous function where that function does not output 0. So that means this whole thing is continuous, and continuity means that the limit exists, and it's equal to the function value, right? Okay, so that's why this exists, and then I use the last part of that sentence I just said, where a continuous function has a limit which exists and is equal to the function value. What is the function value? Well, the function value here means h equal to 0. So if the limit exists and equals the value when h is 0, I can simply replace h by 0 in this expression. And when I replace h by 0, I have g of a times g of a downstairs, which is the same as g of a quantity squared. Good. So, big picture. Let's remind us of what we did. Wrote down definition of derivative, multiplied by 1 to clear denominators, split into two pieces, which was allowed, because both limits exist. G is differentiable, therefore continuous, and 1 over continuous is continuous if the bottom's non-zero. Then used continuity to replace this by g of a squared. So all in all...
Interruption.
Yeah.
Our left side that is currently circled in whatever red-brown color that is, I remember you mentioning that you can factor out the negative, but I don't see a negative in the denominator, so I use.
So I only factored in the numerator, right? So all I did was take g of a minus g of a plus h is minus the quantity g of a plus h minus g of a. So this was purely a manipulation in the numerator with the denominator left unchanged. The denominator, I just kept h from this piece and then put the other guys in this denominator.
I am curious how we went from line 2 to line 3 where the left circled bit that was circled, how we have a negative on the outside then.
Negative on the outside. Do you agree that if I distributed the negative on the outside into these two pieces, then it would give me back the numerator of line 2?
Yes.
And do you agree that if I have any fraction of the form a b over c, that's the same as a times the quantity b over c, where you factor out from the numerator but not the denominator?
I did not know about that.
Ah, okay. Algebra. Good.
Because a over 1.
Yeah, a over... Just think of this as a unit denominator.
Okay.
Good. So this is, in particular, when a is minus 1. I just pull out an overall minus 1 and leave the denominator alone. Good. Other algebra steps in here that are unhappy?
Nope.
Okay. Excellent. Okay, so we have proved the derivative of an inverse. This is the thing we set out to prove. Minus derivative of g over g squared. And I think I have a challenge on this now. So, yaha. Okay, good. So let's use that, and I will ask you to apply that result to fix the fact that we cannot differentiate x with a negative power. So this is a corollary. So we'll use this result that we just proved. The derivative of 1 over g is minus the derivative of g over g squared. And now use this to compute the derivative of f of x equals x to the minus n. So n is still a positive integer, but now I write it as minus n upstairs. So this is like x to the minus 2, x to the minus 1, some term in a Laurent series, for instance. Okay, so we don't have to use the definition of derivative. You can just use this theorem. So what should I write to apply this theorem?
I guess we can start. I don't see anywhere else to go outside of just substituting where we see g for 1 over g. I don't know.
Yeah, I think that's right. Let's be a little clear about what is 1 over g. So we're trying to write f of x equals 1 over g of x for some choice of g. So what is g exactly?
G equals 1 of g? Excuse me, g of x equals 1 over g of x?
Not quite. So we're rewriting this thing. So this is x to the minus n.
Wait, we're creating a new f of x.
We're writing f as the inverse of some function that we know how to differentiate, right? We're writing f as 1 over g, right? So if f is x to the minus n, which is the same as 1 over x to the positive n, then I think we can write f as 1 over g, where g of x is x to the power n, right?
Okay.
Do you remember this, the negative exponent rule, that x to the minus n is 1 over x to the n?
Yes, I'm not seeing our left side now.
You're not seeing our left side. You're not seeing this?
By left side, I mean the entire slide.
Oh, wait, you mean my screen's not transmitting?
No. That is, I'm not understanding, I meant to say.
Ah, okay. Let me say words better. Let me start over. Okay, so, good. So, we proved a theorem to differentiate an expression which looks like 1 divided by some function, right? So, not by, to differentiate something like 1 over g if we know how to take the derivative of g itself, right? So if we know what g prime is, since g prime appears in this formula, now we know how to differentiate 1 over g, right? So now we have a function f of x equals x to the minus n. We don't know how to differentiate this, right? Because we proved a theorem called the power rule, which tells us how to differentiate only when it's x raised to a positive power. So we have no idea how to differentiate this. But we could differentiate if it were raised to a positive power. So we could differentiate a different function, g of x, which is x to the n, right? So the claim I was trying to get you to make is that since we know how to differentiate x to the n, and we're trying to figure out how to differentiate x to the minus n, we can observe that f of x equals 1 over g of x. And then if f is 1 over g, then we can use our theorem, which tells you how to differentiate 1 over g if you know how to differentiate g. This is the strategy. Is the strategy better, or is this still unclear?
I'm understanding slightly better.
Okay, yeah. Maybe it was confusing of me to change notation between f and g, but this is what we're trying to do. So, okay, so, well, let's just plow forward then. So, we'll take the derivative f prime, which is 1 over g prime. So, what should we use using this formula and plugging in the particular value of g? What should we find for the derivative of f?
Well, as you said, according to our formula, we should find that. Thinking. Is it going to be negative g prime over g squared?
Good, so now let's plug in what g prime and g are. So what is the derivative of g at a, where g is this thing?
Is this going to simply be n, I think, negative n x to negative, excuse me, yeah, negative n x to the power of n minus 1.
Good, so that's the top. What's the bottom?
Is this x to the 2n?
Yeah, x to the 2n. Power to a power, multiply. Good. Now, can you divide and use the same base different power rule to simplify this? What do I get?
This is going to be negative n times x to the power of negative n minus 1.
Good, yes. So we just subtracted the 2n from the n, so you got a minus n. Very nice. Okay, so to recap, it was very important that we only proved the power rule for positive exponents. But then we proved this kind of 1 over f rule, and used the 1 over f rule to know how to differentiate negative exponents. And now if we just kind of look at the top left and bottom right with your eyes to connect them, if you look at this, it looks like the same rule actually works. Because if we just naively applied the power rule, even though we hadn't proven it for negative exponents, you would have naively said, well, pull down the minus n, you pull down the whole minus n, and then subtract 1 from the minus n, and you get a minus n minus 1. So in fact, what we've just proven is that the power rule, which before seemed like it only worked for positive integers, now also works for negative integers. We have extended the proof. So now it holds for all positive and negative integers, and trivially for 0.
Out of curiosity, in our original proof of n times x to the power of n minus 1, did we depend on the fact that it was natural numbers anywhere? Or
Yes, for induction, right? Because we proved it works for 1,
right.
and when it works for n plus 1. We didn't prove that if it works for n, it works for n minus 1, right? So you can only induct up, right?
So do any of the other ways of proving not depend on the natural numbers, and you could simply say the integers?
Yeah, I think you could. There's several ways to do it. You can induct in two directions, induct up and down. So that would work not just for the naturals. It would work for the integers. Another way to do it is to prove a formula for the derivative of e to the x first, and then you use a very tricky algebraic manipulation that you write x to the power r for any number r, not just an integer, is the same as e to the power r log of x. This is a very common trick. This is the same just because you could use the power to a power rule and write this as e to the log x to the r, and e to the log x is simply x. So this is a very tricky way to prove the power rule. If you know how to take the derivative of e to stuff, then you just take the derivative of e to stuff and then say, but wait, that's the same as x raised to some power. So now I know the derivative of x raised to some power. And that argument does not rely on it being a natural number or even an integer. So this is another way to prove it. First, I would need to prove for you what the derivative of e to something is, which I have not done yet. Maybe that's a good idea. Maybe we could prove it like that too.
So once you know that, you can unite both proof, well, this current proof and our previous proof of n to the x to the power of n minus 1 into a single one.
Yes, and in fact you unite both those and the proof for rational numbers and real numbers. So for instance, this argument does not tell us how to take the derivative of x to the power 1/2, right? We've only shown positive integers and negative integers. So if someone handed you something and said, or I don't know, if someone walked up to you at the moment and said, well, based on that theorem, I know that this is 1/2 x to the minus 1/2 because you just pull down the exponent and subtract 1. You would say, no, that does not follow from what we've said. We've only proven it for positive and negative integers. But in fact, that is true. The way to prove that is either to use that the square root is the inverse function of x squared and get a formula for the derivative of the inverse, or you can prove it this way with the tricky e to the x shit. So yeah, your comment about uniting is very prescient, because eventually we want to unite these proofs both for positive and negative integers, but also for fractions and for any real number. Good.
Oh boy.
Hola. Good. Other comments or thoughts?
Nope.
Okay, I think, yeah, the last part will go faster, so even though there's 15 slides left, we might still finish at a decent hour. So, oh yeah, this is the solution, but let me just read it again to make sure I understand what's going on. So, right, so we wanted to extend our proof for positive integers to negative integers, so we wrote f of x is 1 over x to the n. We've shown that x to the n is differentiable whenever x is non-zero. Or here we're valuing it a, so if a is non-zero. Then as we saw, we apply the formula, the derivative of f, which is the derivative of 1 over g, is the same as minus the derivative of g over g squared. The derivative of g, by our previous proof, since g has a positive exponent, that's nx to the n minus 1. Downstairs we have x to the 2n, as you say, and then you simply use the power rule for division. division of two numbers with same base, different powers. And yeah, as we discussed a moment ago, now we've shown the power rule works for negative integer powers. We have not proven it for rationals or reals. Okay. Now the third part. Oh, wait, no, there's one more part in Act 2 before we move on to Act 3. So, actually, this is more important than the 1 over f rule. So this is something that if you take AP Calc, for instance, at the exam, they expect you to have this memorized. So this is slightly more general. You might ask, well, you told me how to differentiate 1 over g. So that's just 1 in the numerator and a function g in the denominator. You could naturally ask, can you extend that result and tell me how to differentiate an arbitrary quotient, a function f upstairs and a function g downstairs? How do you take the derivative of that quotient? And we can do it. It's actually almost a corollary because it follows very easily from the previous result. So first, here's the statement. Derivative of f over g is derivative of top times the bottom left alone minus the derivative of the bottom times the top left alone over the bottom squared. So I find it useful to have these little chants because you have to have all of these in your brain. So for instance, the product rule, remember, was derivative of first times second left alone minus plus derivative of second times first left alone. Derivative of top over bottom is derivative of top times bottom left alone minus derivative of bottom times top left alone over bottom squared. So if you make these little sentences in your head, I think they're usually easier to memorize, but the only reason to memorize them is because exams and other classes will expect you to have them memorized. More important is understanding the proof. So let's understand the proof. It's quite easy. You notice that a fraction of two functions, f over g, is simply the same as taking f and multiplying it by 1 over g. Right? This is, if you prefer, f over 1. So that's nice because we already have a product rule. We already know how to take the derivative of function 1 times function 2, and we already know how to take the derivative of 1 over g. So let's just use those two things together. Here we go. Derivative of f times 1 over g, so f times 1 over g prime. The product rule is derivative of first one times second one left alone plus derivative of second one times first one left alone. That's the product rule. Now we just plug in. The first one, there's nothing to do. You simply put f prime upstairs and g downstairs. The second one, we use our previous result. So we proved the derivative 1 over g is the same as minus derivative of g over g squared. So here all I've done is substitute the two purple circled expressions, which we proved on the previous slide. And now the algebra challenge for you. What algebraic step do I use to go from line 2 to line 3?
I guess I'm going to throw out a random idea. Perhaps we have to square the first fraction?
Square the first... So why are we allowed to take the square of something and say that doesn't change it or something? Maybe I should ask for clarification. What do you mean by squaring?
Put the top and bottom to the power of 2.
So is that an algebraically allowed step? If we're adding up two fractions, a over b plus c over d, are we allowed? Yeah, we can't just square stuff in general. That's not going to be the same.
I don't even know.
Let me write it more suggestively, because the denominators are very similar, but one is the square of the other. So how do you simplify a over b plus c over b squared? What's the usual way to simplify this? And the hint is multiplying by 1 in a particular place, in a particular form.
Are we going to be multiplying by g of a over g of a?
Yeah, good. So in particular, in the first term, f prime of a over g of a times g of a over g of a. So your idea in the first step of squaring was almost correct, but we're not allowed to just square stuff in general. However, we can multiply by 1 in a form which squares the denominator, right? So if I do that, multiply by g of a over g of a in the first term, that gives us f prime g over g squared, And now the denominators are the same. Two denominators with g squared, so you combine these two things with a common denominator. F prime g minus g prime f over g squared. And that's the proof. Thoughts on this or other algebra questions?
I have no thoughts or questions.
Good. Eventually you'll get to the point where you look at an algebraic equation and even without being asked, your brain will automatically start looking for ways to multiply by 1. Kind of like when you rub your eyes and start seeing stars everywhere, you'll just see, f over f, like a little star appear. A form.
That isn't just me.
What'd you say?
That isn't just me who just pushes your eyeball and looks for the light.
Yeah, it's kind of amusing. Little stars showing up. It's also very similar. Have you had the experience of playing a video game for a long time that has like a health bar or an ammo counter, and then you just go walk around in real life and there's like ghosting? Like you see the health bar in real life, kind of, not really there, but you think you see it there. You know what I mean?
I've had a similar thing with noises, not quite with visual.
Oh, that's interesting. So you hear game noises in real life?
Yep.
I see. I see the ghosted health bars, but the ghosted health bars are like, g over g just appearing here to multiply by. They just, I don't know. Makes it easier to find the algebra when, you see them ghosting. But, okay, last question in Act 2, then we will do Act 3. So the hint is we're using the quotient rule, but the first part of the challenge in this question is figuring out how to write this as a quotient. So, question, suppose a is non-zero, and our function f of x is x squared times the cosecant of x. How do we take the derivative to get f prime, the slope of the tangent line, at some point a, which is not 0? What do you think?
Well, I'm trying to Google cosecant because I can't remember it, but my phone's going slow.
La 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 la. Well, let's see. We remember...
Okay. That gives me no information. Good job, Google.
Remember the way to remember these?
Yeah.
So, yeah, they come in pairs, and each pair has one co between them. Secant and cosine, cosecant and sine. So cosecant should be 1 over sine, right?
Yeah.
Okay. Now let's see if you can remember the mnemonic from the previous slide. How do I take the derivative of this?
Okay, this is to be on the top we have, let me think, square times sine x minus, right?
Wait, what was the first part you said?
I believe so. Oh wait, never mind. Okay, the first part is going to be x squared minus, no, that wasn't right at all. X squared times sine x.
X squared. So which one did you differentiate here?
Oh wait, that's a prime, not a 1.
Mm-hmm.
Why did I hesitated and with my old answer because I couldn't tell. I'm so...
It's okay.
Anyway. So, we're going to be differentiating, I believe, x squared.
Okay.
Seems right. And that is going to be 2x times sine x minus, thinking, x squared times cosine x?
Good. And the denominator.
Over... Is this going to be sine squared x?
Yeah, denominator squared. Good, okay, yeah. Here's derivative of top times bottom left alone, correct, minus the derivative of the bottom times the top left alone, also correct, all over bottom squared. Very good, yes. It's, kind of messy, but, much of, as I say, there's nothing theoretically interesting about taking derivatives of functions like this, but, I mean, when you're doing a physics problem and a, particle is moving with a velocity given by a particular function, or a force has a particular form, you need to take derivatives of stuff, and it has to be as automatic as multiplying. So things like this have to become second nature. So this is good.
Quick note. I like how the Atkins book refers to, like, for example, potential energy and force and stuff as a particle and not an object. Is there? I get that it can be a single particle, but why is it worded like that?
I think this is because in classical mechanics, so in physics, when you study the dynamics of particles and objects, you begin by studying how a point behaves, because if you have a single point and it's acted upon by gravity, for instance, it has some force or some potential energy, then this is a simplifying assumption, because a point has no shape. A point simply moves downwards under gravity, and you don't need to worry about any complicated effects because of the fact that this point actually has some shape or structure. Later in physics, you start to study the dynamics of extended bodies. So if I have, say, a plate or a saucer, so here's like, I don't know, a plate, and a plate is falling under gravity, there's going to be a much more complicated dynamical system that describes the motion of this plate, because although the whole thing is moving downwards, there's also going to be some wobbling, so it's kind of rotating, and maybe it wobbles like this, and then there's some angle that you have to measure to tell how much has it wobbled at each point in time. So studying the dynamics of an extended body like a plate or, say, a rod that can rotate as it falls, that's going to spin as it falls, this is much more complicated. So in general in science, whenever you're studying an object where the specific shape is not super important, say an atom, right? If you're studying a single carbon atom and how it moves in some, I don't know, some force field, the shape of the atom is not especially important, so you can pretend it's just a point with no shape, a point with no extent. It's like an infinitely tiny object, and just say, this is the way that a point particle moves in a potential or under a force. That's the point. No pun intended. The point of points. Is that the question? Is that what you're asking?
Okay, I see now. Cool.
Okay. It's actually very important. I mean, even for gases, like O2. So if you have a gas, 2 oxygen atoms making a molecule, they actually act like it's 2 particles with a spring between them. So even if you want to study oxygen in a potential, the whole oxygen thing moves around, but also they kind of, maybe the 2 oxygen atoms get closer together, so the spring gets compressed. It's very complicated even with 2 particles tied together. Anyway, I'm rambling now. I'm curious, though, you preface that sentence by saying you liked how Atkins said particle rather than object. Why do you like the word particle better? I'm curious.
Did I say like? I meant to say noticed.
Okay. I thought you were expressing a preference for the word particle for some reason. Good. Other questions on quotient rules or falling plates or springs?
Nope. Should probably get back to work.
Yes, okay. I mean, we started 90 minutes ago, so I think we can finish in the next half hours.
Wait, we didn't finish that one.
This one? Yeah, we're done. You gave me the answer, right?
Wait, that was it?
Yeah, that's the quotient rule.
Oh, okay.
Oh, what did you want to do? Simplify it or something? Or you thought there was another step?
There was additional simplification to be done.
Oh,
yeah.
I mean, sure. If you want, you could write this as, I don't know, 2a over sine a minus, I don't know, a squared cotangent a. I don't give a fuck. I mean, it's the same thing.
It just makes it even more complicated.
Yeah, I don't really. Often, I don't really believe in simplification. Often people come out of an algebra class saying they believe there's a standard way to simplify stuff. You always have to write things in a most simple form. There is no such thing as a most simple form. The most convenient form depends on your applications. So for the purposes of computations we do in this group, I mean, unless you know that this thing will simplify massively, all of this will cancel, there's no reason to try to massage stuff to get it to a most simple form. I mean, basically anything which is algebraically equivalent to the answer is fine. Good. Onward. Last piece. Questions on the first 2 sections before we do the chain rule?
Nope.
Okay. So, you may get the impression that we still cannot differentiate most functions because we've only done very limited cases like product rule, quotient rule, and so forth. And you know that the most interesting functions you can think of are typically composites, right? You compose two functions. So the classic example is if you take something like a trigonometric function, say sine x, and another function like a polynomial, say x squared, you can compose these to get much more interesting functions. And you remember the notation is to write a circle between them. So f circle g, or f composed with g, evaluated on x, is simply the same as f of g of x, right? You plug the inside into the outside. So similarly, g of f of x. I now realize I'm writing the same thing that's already on the slide. I don't know why I'm doing this, but this is composite. And you proved on consolidation document 2 that if a function is continuous, actually there were slightly weaker assumptions, only one of them had to be continuous, but for our purposes it's enough that if f and g are both continuous, then their composite is continuous. So we know continuity works nicely with composition, but we know also that not all continuous functions are differentiable. So you might ask, how does differentiation play with composition? In other words, if you want to differentiate f of g of x, which in this case is plugging x squared into sine, which gives us sine of x squared, what's the derivative of sine of x squared? Or you could go in the other order, say we're going to plug f into g, so you plug sine of x into the squaring function, and plugging sine into squaring gives you sine squared. So how do you differentiate sine squared of x? We don't know how to do that yet. So we need a new theorem that will let us differentiate these arbitrary composite functions, but the proof is a bit hard. So this is, I think, probably about as hard as when we proved the intermediate value theorem. And you'll remember I offloaded that proof. We put it into a separate meeting called 3 hard theorems or 3 hard proofs or something, because it was a bit more involved. So I'm going to do something which is a bit irresponsible and ask you to just accept that the chain rule is true for now, and we'll use it to solve some problems until we become fluent with using it, and then we'll come back and prove it. Or maybe you'll prove it in CD3. I don't know. Someone will prove it. Good. Questions on this or on composition or anything?
Nope. What is the chain rule?
Good. What is the chain rule? Here's the theorem. Last one. No, not the last one. You have to memorize.
It doesn't make any logical sense, but okay.
What I wrote down doesn't make sense?
Fair.
Okay. I will explain.
It's not obvious.
So, but wait, by not make sense, you mean you don't understand the expression, or you don't see why it should be true?
The latter.
Oh yeah, this is totally non-obvious. Like the derivative of a sum was pretty obvious. You would think the derivative of a sum should be the sum of the derivatives. This is not at all obvious. That's why the proof is hard. I look at this and I don't have the proof memorized, so when I look at this, it's not at all clear why this should be true. But all this is saying, what this is saying is that if you have a function which is f of g of x, this big old function, and you want to prime that whole thing, you kind of have to do it in layers. You peel off the outer layer, the f, and prime that guy. So the first thing you do is f prime, this is priming the outer layer, and the inner layer stays the same. So f prime of g, I'm going to use a, well, yeah, fine. I'll use x in this line, even though I used a on the previous line, whatever. So you do the outer, prime the outer guy, and then you peel off the f and multiply that by the prime of the inner guy, g prime of a. So f of g of x differentiates to f prime of g of x. Now I changed from x to a. F prime of g of x times g prime of x. So again, the peeling thing I just told you is a mnemonic. This is just as bad. I'm being very shitty when I say this. This is just as bad as the mnemonic for remembering the power rule, which is pull down the exponent and subtract 1. This tells you nothing about why that should be true. So the peeling off thing is not a proof or an explanation at all. It's just a way of remembering. But I claim we will do the proof, so I'm not as bad as I could be. But anyway, okay. This is the statement. It probably doesn't make a lot of sense until you see an example. So instead of just jumping into a challenge where I ask you to apply it, I will give you an example. So let's go back to the thing that we did before. Sine of x and x squared. So let's first compose them in the f of g of x order. So we're going to differentiate f composed with g at a, and we use the chain rule, so it's f prime of g of a times g prime of a. What's f prime? F is sine x, so f prime is cosine x, but remember it's f prime of g of a. So we have to plug into the cosine function whatever g of a is. What's g of a? Well, that's a squared. Good. So the first factor is cosine of a squared. This is derivative of f, plug in g. Peel off the f, what's left? Now we have to differentiate g. G prime, well, we know how to differentiate x squared, that's 2x. At a, it happens to be 2a. So the chain rule says this whole derivative should be cosine of a squared times 2a. Let's go in the other order. What if we instead differentiated the function g composed with f? So let me just well, maybe I should write what this function that what did we just take the derivative of? Up here, f composed with g was sine of x squared. So if you take the derivative of that function, you get cosine of a squared times 2a. Now we're going to differentiate a different function, which is sine squared of x. That's what we're differentiating now. So how do you differentiate sine squared of x? Differentiate the outside function, which is g. So g prime is the derivative of x squared, which is 2x, but you have to plug in for x sine. So that factor is 2 times sine at a, or 2 sine of a. Multiply by the derivative of the inside function. The inside function is sine, and the derivative of sine is cosine. So this one is 2 sine a cosine a. And now you see that the order in which you compose is very important. F composed with g and g composed with f have very different derivatives, and they're very different functions. So, good. Important. Questions on this chain rule example?
I have no questions.
Alright, now we'll see how quickly you can blitz 4 examples where you have to use some combination of those rules. So, well, hopefully you remember them all. Let's go. First one, chain rule example. Sine of x plus x squared. How do I differentiate this?
Oh boy. Let's see, this is going to be... Suddenly struggling. Okay.
So the outside function is sine, right? So start with that.
Oh, wait. Okay. I totally skipped over the sine. So this is going to be cosine of x plus x squared?
Yeah, so yeah, we're plugging in x equals a. So cosine of a plus a squared is the first part, and now multiply by what? So this should be the derivative.
I'm trying to remember.
So
I forget if is it just g of a?
g prime. So it's the inside guy differentiated.
Okay. So 1 plus 2a.
Good. 1 plus 2a. Yeah. Derivative of outside with inside left alone times derivative of inside. Good. I will show you that again. So just for the first example, I will write out carefully what the inside and outside functions are. So the outside function is sine, because this is sine composed with x plus x squared. So the outside function is sine, the inside function is x plus x squared. We're supposed to take derivative of outside with inside left alone times derivative of inside. Derivative of outside with inside left alone, as you say, is cosine of a plus a squared. Derivative of inside is 1 plus 2a. So the product is cosine of a plus a squared times 1 plus 2a. And I've now shown you how to do this in Mathematica. I think for some of the daily challenges, they'll ask you both to compute the derivative and then attach Mathematica code to check your derivative. So the way to take a derivative in Mathematica is very simple. Just use the letter D, capital D. Derivative. Yes, you want the D. So capital D on the function sine of x plus x squared that we want to differentiate, and then you put a comma and the variable name. So the variable that we're differentiating with respect to is x. So d of sine x plus x squared. That will give you, if you plug in, if you ask Mathematica that, the way that I wrote it without this junk on the end, if you do that, it will just return cosine x plus x squared 1 plus 2x. So that gives you the derivative with x instead of a. If you want to plug in a particular point a, which is the way this problem was phrased, you just put an additional thing at the end to replace x by a. And then we get what we found before. Very simple, just d. Okay, questions on this blitz?
Nope.
Good, more. Alright. 1 divided by the quantity 2x plus 3, all cubed. So I think we need the quotient rule, or possibly the power rule and the chain rule. You have your choice of ways to do this. I suggest using the power rule and chain rule, if you can see how to do it, because that way is much easier. So I'll ask you, how should we differentiate this?
So I believe that this is going to be, let me think. I guess start by bringing, within f of x, we bring our 2x plus 3 to the power of 3 to the top to get 2x plus 3 to the power of negative 3.
Good. So 2x plus 3 to the power of negative 3, and we proved that the power rule works for negative exponents, so we are still kosher. Alright, what's next?
Kosher. Lovely. So this is going... I guess we can break this into two functions where g of x equals 2x plus 3 and h of x equals x to the power of negative 3.
Yeah. Yeah, that's perfect. So the outer function is x to the minus 3, good, and the inner function is 2x plus 3, and this is the composite of them. Good. So, how do you chain that bad boy?
I need a minute to walk upstairs quickly, if you don't mind.
Okay. Good.
Alright, I'm in a quiet place once more.
Not like the movie A Quiet Place, though.
Fortunately.
Good, okay. So
Alright, let's see.
So you were telling me this is a composite where the outer function is raise the thing to the minus 3, and the inner function is 2 times the thing plus 3, right?
So I believe that we proved previously that the differential of a I'm out of breath for walking upstairs.
Dude, don't you run like 6 miles? How are you out of breath from walking upstairs?
I don't know. So we have proved previously that the differential of something to the form along the lines of mx plus b equals, I believe it is just m. So therefore, differential of h of x where, g of x equals 2x plus 3. G prime of x equals 2.
Yeah, so you say the inside function is 2x plus 3, and the derivative g prime of x is 2. You can either see that by appealing to our mx plus b result, or you can use the power rule, because you can think of this as 2x to the 1 plus 3x to the 0. So this is 2 times, well, pull down a 1 and subtract 1, you're left with 0. This guy gives you 0. So you can either use the line thing or the power rule. That's fine. Okay, so we use that, and then our outer function was what, h of x equals x to the minus 3. So now what?
And that is going to be negative 3 times x to the 2.
Good. Minus, oh wait, careful, subtract 1. So x to the minus 4.
Right.
Okay, so now I've intentionally written these two functions so that I didn't tell you which one is inside and which side is outside, because one of these we have to plug in the inside again. So how do we chain rule this thing? Well, first question is which is the outside? Oh, sorry.
Is it? So this is going to be. That doesn't look quite right. Is it negative 3 times 2x plus 3? The power of negative 4?
Good, so that's derivative of outside with inside left alone, and we multiply by what?
2.
2, good. So, yeah, this is right. You can also rewrite it, if you want to put this guy downstairs, you could instead, if you want, rewrite it as this. But that is correct, assuming the downstairs is non-zero, of course, so if x is not minus 3 halves. Good, so this is the derivative with the chain rule, which is the faster way to do it. And as you say, we just differentiate the outside. Minus 3 minus 1 gives the minus 4. Leave the inside alone.
Did you, like, literally solve right there what x is hopefully not going to be?
Oh, for the denominator? Yeah, minus 3 halves makes the denominator 0, right?
Okay.
X is not minus.
Makes sense. Oh my god, I'm dumb.
I mean, hopefully you're good enough at algebra to solve that one in your head. If even I can do it, I'm not very good at algebra. I probably should have
Anyway.
Good. Yeah, so this was the answer we had in the previous slide. And here's how to do it again in Mathematica. Give it a d, 1 over 2x plus 3 quantity cubed, comma x, and you get this thing. So it's always good to be able to check. You should be able to compute these yourself, but as a way to learn Mathematica, since I added Wolfram Mathematica as a CV line item, you should know how to take derivatives in Mathematica. Good. Questions on Blitz 2? There are 2 more. Almost done.
I have no question.
Excellent. Alright, back to the sinc functions. You remember this from a while ago? We looked at sine x over x as the sinc function, which is short for sinus cardinalis, this cardinal sine function, which I think is a very cute name. So we will need the quotient rule. What should I do to get the quotient, the product of, the derivative of this quotient? What do I do?
First, a comment on cardinal sine.
What is the comment?
That is almost identical to cardinal sin.
That's funny. I never even noticed that. I'm just gonna write it like this with a parenthesis because I like cardinal sin better.
Thinking. So we can let one of our functions be let g of x be equal to x to the power of negative 1, or 1 over x, however you prefer it, and let h of x equal sine x.
Okay, you're using the product rule, so you want to do this as sine times 1 over x, you say?
Yes.
Okay, yeah, that's fine. Good, then what do we do?
Or is there a more efficient way?
No, I mean, you could do it either way. So you're saying g of x is sine x, and h of x is x to the power minus 1, and then you're saying use the product rule on gh, which is totally legit. You can also use the quotient rule, and use upstairs is sine, downstairs is x, and use the quotient rule, but they're exactly the same, so this is fine. What do we get from the product rule then?
So because all of these get called f of x originally, I'm remembering the mnemonic doesn't help much. So I need to get used to renaming things.
That's why I say first and second, right? Product rule is derivative of first times second left alone plus derivative of second times first left alone.
Lovely.
It's better than f and g, right? Because then you don't get confused. You'll notice I also did that in my quotient rule mnemonic. I said derivative of top and derivative of bottom, and in chain rule my mnemonic is derivative of inside and derivative of outside. So, yeah, I share your struggle.
Oh.
Go on.
Are you lagging?
Maybe. I've heard silence for like 30 seconds, so either you're thinking hard or I'm lagging.
Yeah, I've been talking for like 20 seconds.
Oh shit, I'm sorry. Can you repeat whatever you were saying?
So, I believe that the first part of what we have is going to be sine of x to the power of -1.
Sine of x to the power of -1, you say?
Ah, wait, I meant to say cos.
Ah.
Yeah, first time around.
So I think it should just be cos x, not cos of 1 over x, right? It's not a chain rule, it's a product rule.
Oh.
Right. So remember, yeah, you don't plug in the second one into the first one for the product rule, but you do for the chain rule, right? So, more explicitly, gh prime at a, the rule is g prime of a, h of a, plus g of a, h prime of a. So for the product rule, both of them get evaluated at the same place, right?
I think I was using the chain rule. The composed function that I was using are the ones that we have listed to the right already.
Ah, but composing these does not give you f, because if you compose, in either order actually, if you compose g of h of x, then that means plug in h into g, so that would give you sine of 1 over x, which is not the same as sine x over x. If you go in the other order, h of g of x, that means plug in g to h, so plug in sine to 1 over x. This gives you 1 over sine x. But neither sine 1 over x nor 1 over sine x is the same as sine x divided by x. They're all different functions. Catch my drift?
And now I need to think about...
Oh, sorry, you cut out. You have to think about what?
But I messed up.
Ah, well.
I was aiming to use the chain rule.
Yes, okay. So, don't do that, but is it clear that these three functions are inequivalent, though?
Yes.
Okay. Alright, back to the drawing board then.
Though necessarily, I was thinking g of x times h of x gets... that isn't quite the right thinking.
G times h is indeed what we want. G composed with h is not what we want.
Does g times h have any relevance here?
Yeah, G times h is f. That's exactly what we want, right?
Okay.
Yeah. This guy, that's good. And G composed with h is not f. Okay. Do you have
But
an...
now I feel the need to see... No, seeing the chain rule again.
You want to go back and see the statement of the chain rule?
I guess so.
Okay, hold on, let me hide the... I realized I can hide without deleting everything, so... This was the statement of the chain rule.
I totally ignored that it was function composition that was, like, on the left side.
Yes, very important. This is plugging g into f, not multiplying them. So that's why in our example, for instance, for sine x and x squared, this is composing f with g, which was sine of x squared, not sine of x times x squared. Good. Or in this one we composed. So sine of x plus x squared is different from sine x times x plus x squared. Composition, not multiplication. Good. Alright, back to this thing.
So it seems like we should be able to insert g of x into, we should be able to insert g into h. And that is equivalent to f of x.
Insert g, by insert g into h you mean compose h of g of x?
Correct.
So, oh, that's not what I want. Whoops. Pen. So I think that's not the same as f, because h of g of x, so if you insert g into h, then this gives you 1 over sine x.
Oh, right.
Yeah. So I don't think we want to insert anyone into anyone. This is should be a product of g and h, right? I came out sounding much worse than I wanted it to, but I tried to roll with it.
Bump.
Bump.
Blowing on the microphone.
Oh, am I whooshing again like last time?
Nope.
Good.
Okay, so I guess I did. I'm just gonna go with the product rule because I already have two things at work.
Yeah, okay. So
It's going to be GH quantity prime is going to be equal to thinking. I mean, we have it there.
sorry, I'm being a troll.
So this is going to be cosine of x times, cosine of a times a to the power of -1 plus sine of a times negative times x to the power of -2.
Good. Minus x power minus 2. And we can simplify this a little bit because I'll just put all the minus powers downstairs. So this is... did I just put an x? Damn it. Sorry. See, this is a problem with asking whether something is at x or at a. So cosine a over a minus sine a over a squared. Good. And now we see that if you wanted to simplify this and get a common denominator, then you get what we would have found from the quotient rule, right? So now you see why your approach using the product rule was the same as the quotient rule, because the quotient rule would have said, well, you want derivative of top times bottom left alone, which is this thing, minus derivative of bottom times top left alone, which is this one, over bottom squared. So product rule and quotient rule give the same answer, which is comforting, because if you prove the two things are true, they should both be true. Good. Questions on this?
I do not have any questions.
Okay. I couldn't tell if you were getting tired or if you were just very unhappy because you really wanted to use the chain rule and were upset when it didn't work. Okay. This is just confirming that the answer you wrote down a moment ago is correct, and then again showing how to do it in Mathematica, D of whatever. You can always wrap that bad boy into simplify to get a common denominator. But, good. Last thing. Sine of x. Let's see. How should we differentiate sine of x?
Okay, by function composition, let g sine of x and h equals sine of x.
Good. So g is sine and h is sine. So what do we get when we chain that pair?
So this is going to be cosine sine of x.
Cosine of x. And
times cosine x.
That was
A.
so this one I didn't give an A, but if you prefer, I'll put all of them at A. I've been switching the notations. There's 3 notations: f prime of x, f prime at a point A, df dx, which is at x, and then there's a 4th notation, df dx, with a vertical bar A. So there's several different ways of writing it.
Wait, does the vertical bar just say replace all with some, or is there other meaning to it?
The vertical bar always simply means replace the independent variable x with whatever appears on the bar, A. That's all it's for. It's very weird. Yes, but thankfully we do not need that here. Well, I could write it that way if I want, but the vertical bars I think are quite strange. So this is the derivative of sine, which I think where does this come up? I've only seen iterated sine functions come up like 2 or 3 places in physics. It actually comes up less than you would think, but good. So let's verify that we didn't make a mistake. Indeed, by the chain rule, differentiate the outside sine, get a cosine, leave the inside sine alone, multiply by the derivative of the inside sine, which is the cosine, so it's cosine of sine of x times cosine of x. And again, Stephen Wolfram agrees. Just hit that with a D, and then you get an x.
I know one place that sine of sine comes up a lot.
Where?
In board geometry classes.
Board, as in like you just plot it to see what it looks like?
With their calculators.
Ah, you're probably right. Yeah, you've probably plotted this in Desmos, which you tell me about.
That's a great idea.
And now you can plot it in Mathematica, and you can make it colorful, or you could do a 3D plot. So the world is your oyster. Okay, so that's the end for today. I apologize for the kind of tediousness of applying these rules. We'll probably have 1 or 2 sessions where we need to build up a few more rules, like we'll need the derivative of an inverse function. We'll need the derivative cosine, derivative of e to the x, derivative of log, derivative of tangent, blah, blah, blah. So you have to know all of these so you can... So when you take the AP Calculus exam and they ask you to take, what is the derivative of e to the x squared secant x over tangent cubed of x? They'll just play function fucking bingo and give you some strange combination of functions and ask you to take the derivative. That's racist to the minus pi over 2 power. Just